Hey everyone! So today we're plugging into the one piece of tech that's absolutely driving our green future, the lithium-ion battery. Right? They're in our phones, they're in our cars, and now they're in these massive systems that are starting to power our entire electrical grid. But as we race towards this cleaner tomorrow, you have to ask, what are the hidden risks we're building into our world right now?
And that whole journey for us starts with a question that, on the surface, sounds pretty simple. How do you actually put out a battery fire? Well, as we're about to see, the answer is anything but simple. Okay, take a look at this number, 150,000 liters. I mean, that's almost enough to fill a small swimming pool. But in the world of firefighting, this number represents a huge and, frankly, a growing challenge. And here's why. The difference is just staggering. Putting out a fire in a regular old gasoline car, that might take, say, 3,000 liters of water. But in an electric vehicle, data from around the world shows it can take up to 150,000 liters. That is 40 times more water, all to fight a fire that just refuses to die.
And look, this isn't some far-off what-if problem. This timeline shows you recent incidents that happened right here in Taiwan, all involving these big, large-scale battery storage systems. From Taipower facilities to private ones, these high-tech fires, they are already a reality for our first responders.
So this brings us to the core question of this whole explainer. Why? What on earth is happening inside these batteries that makes them burn so intensely, for so long, and just laugh off our normal ways of fighting fires? To really get that, we've got to dive into the chemistry.
And the answer, the key to all of this, is a powerful and really dangerous process with a deceptively simple name, thermal runaway. This is the whole ballgame right here.
Okay, so what is it? Thermal runaway is basically an unstoppable chain reaction. Once it gets going, it just keeps generating its own heat, feeding itself over and over, and getting faster and faster until the battery literally destroys itself from the inside out. This isn't just a fire, it's a full-blown runaway chemical event.
So here's how it goes down. It all starts with the trigger. Some damage or a defect causes a short circuit. That creates heat, which starts breaking down the chemistry inside, and that releases flammable gases. Okay, so that's your fuel. But here's the critical part, the real game changer. As it gets hotter, the cathode material itself disintegrates and releases its own oxygen. All of a sudden, the battery has both the fuel and the oxygen sealed up inside it. It becomes its own little self-contained, self-fueling inferno that you can't just smother.
All right, so now that we get the wild science behind the fire, let's zoom out a bit. Why is dealing with this risk so incredibly urgent right now? Well, it's because we are becoming massively reliant on this exact technology.
To hit our 2050 net zero carbon emissions goal, Taiwan is betting big on renewables like solar and wind. But, the sun isn't always shining, the wind isn't always blowing, so to keep the grid stable, we need a way to store all that energy. And our number one solution? You guessed it, massive banks of lithium-ion batteries.
And the scale of this bet is just enormous. By 2025, the goal is to have 1,500 megawatts of battery storage capacity. Just 5 years after that, by 2030, that number is supposed to jump all the way to 5,500 megawatts. I mean, that is an incredibly fast expansion.
So the crucial point here is that this isn't just about the electric car in your driveway anymore. We are building this exact fire risk into the very foundation of our national power grid. These things, these battery energy storage systems, or BESS, they're becoming a totally fundamental part of how we keep the lights on every single day.
But the danger doesn't just stop when the flames are eventually, put out. There's this invisible and, honestly, often overlooked consequence that can stick around for years, and that's the toxic aftermath.
Remember those 150,000 liters of water we talked about? Well, when it floods that fire, it doesn't just disappear. It mixes with all the burned-out guts of the batteries, and it becomes this toxic soup that carries all these hazardous materials away from the fire and out into the environment. And what's in that soup? Well, it's a nasty cocktail of pollutants. The electrolyte salt reacts with water to create highly corrosive hydrogen fluoride gas. The cathode and the anode, they release heavy metals like nickel and cobalt into the water. Even the plastic casings release their own pollutants when they burn. And now research is flagging new worries like PFAS, the forever chemicals. And just to put the danger of these gases into perspective, check this out. Based on scientific research,
A single burning battery pack can release enough hydrogen fluoride to reach concentrations 80 to 800 times the level that's considered immediately dangerous to life or health. That is an extreme hazard for anyone nearby.
And all that toxic water has to go somewhere, right? It just seeps into the ground, contaminating the soil and the groundwater, carrying those heavy metals and chemicals far away from the original fire. And this creates a really long-term risk to local ecosystems, to agriculture, and yeah, potentially to our health.
So, what's being done about all this? Well, faced with this totally new high-tech threat, our first responders are having to innovate and adapt at, like, lightning speed.
You know, just recently, 144 firefighters from 17 different counties, all across Taiwan, got together for this special seminar focused entirely on how to respond to EV and battery emergencies. This just goes to show you how seriously the firefighting community is taking this new, evolving challenge. And one of the key questions they're asking really puts you right in their shoes. If we spray thousands of liters of water onto a high-voltage battery, are we going to get electrocuted? Now, the answer, thankfully, is that the risk is pretty low. The car's safety systems are designed to cut the power, and their gear helps protect them. But the question itself just reveals the complex new dangers they're up against.
And because of that, their toolkit is changing fast. The traditional fire hose is now just one tool among many. They've got specialized gear like these heavy-duty fire blankets, special nozzles made to spray water up and cool the battery from underneath, thermal cameras to see if it's going to reignite, and even AI-powered robots for fires that are just too dangerous to get close to.
Okay, so fighting the fire is one thing. But the ultimate goal, of course, is to prevent it from ever happening in the first place. And that brings us to our final section, the global search for a safer battery. And believe me, the race for solutions is on. You've got policymakers working on tougher rules for where you can even build these massive battery farms. At the same time, scientists are working on totally new designs, like solid-state batteries that don't even have a flammable liquid inside, or flow batteries that store energy in a completely different, much safer way. And all of this leaves us with one final question. Our clean energy future, this battery-powered world, it's not coming anymore, it's here. The benefits are obvious, but so are the risks. The real challenge now is making sure our safety rules, our emergency response, and our technology can actually keep up with our ambition. So the question is, are we ready?